Hey there. So in this lesson, let's revisit that random surfer model, but this time from the perspective of linear algebra. Why? Well, if you can formulate a calculation in terms of linear algebra, then that will lead to a compact and efficient way to implement it. Well, at least usually. Okay, so let's see how that works. Now recall the problem of a random surfer traversing a graph. The chance that he or she is on a given node I is given by this summation. For all nodes j that go to I, the product of xj of t minus 1 and p sub ji. Now let's consider the xi of t and xj of t minus 1 to be variables. Now let's take a look at the xi of t and xj of t minus 1 variables. Define a column vector, x of t, whose entries are all the individual xi of t variables. Next, consider the transition probabilities, pji. Let's represent these in a table or a matrix, capital P. Let's use the convention that element pij resides in row I and column j of this matrix. Now from this notation, you can write down a simple matrix model of the surfer's behavior. X of t equals p transpose times x of t minus 1. Take special note of the transpose. Its presence is a consequence of two conventions. First, x of t is a column rather than a row vector, and pij is row I and column j of p. Now the matrix equation helps us in a few ways. First, suppose you expand x of t minus 1. You'd get p transpose times x of t minus 2. In other words, p transpose squared times x of t minus 2. Now continuing, you would get p transpose to the power t times x of 0, which is the initial distribution. One important note, this form of raising the matrix to a power is helpful mathematically, but you should not calculate it this way. Instead, you should start with the initial distribution. Then, in a loop, you do something like the following. Multiply the current distribution by p transpose and then repeat until done. Now, you should pause for a moment and think about why this approach is better than the first one of raising p transpose to the power t. Now, linear algebra also allows for mathematical analysis of this process. So for example, let's consider the following question. Does this process converge? That is, in the limit of t goes to infinity, is there a finite limiting distribution? The answer is a resounding yes, and that stationary distribution is unique. Now the reason it's technical, but it stems from two facts. First, that the columns of p transpose sum to 1, and secondly, from a result known as the Perron-Frobenius theorem. We'll post some notes so you can read more about it. So to conclude, viewing the problem as a linear algebraic one helps us in two ways. One is theoretical, and even though we skip the details, you can use the mathematical tools from linear algebra to show that this stochastic process has a well-defined limit. So put differently, we can estimate how likely the surfer is to be on any given node, which we can then interpret as a ranking. Now the other benefit is practical. If you can form the matrix and the vectors easily, then you can use off-the-shelf linear algebra functions to write a compact and efficient implementation. So go back over what we just did, and when you return, we'll talk about one last implementation detail before coding up the analysis.